Good morning, I'm Peter from Aruba, and I'm going to talk about one of my interests, which is mobile devices and what they do on mobile networks, on Wi-Fi networks, and what they should do in the next year or two. Some of you may have seen this before. Hopefully the ones who have gone next door, because apart from a couple of new jokes, which I may forget to drop in, it's going to be pretty much the same as you may have seen at Airheads. I'm going to start off with a demo because I like living dangerously. And let me just explain what it's going to look like. If I come over here. So this is a little app that I wrote. It is up on the Google Play Store, if you don't mind some self-promotion. We're showing signal strength here, RSSI. And it just moves back every 2 seconds. And up here, we've got a channel number. We've got some RSSI figures and a data rate. Down here, we're showing signal strength from the scans. So every 5 seconds or so, it scans. And you'll see the signal strength of the different APs. The thick one is the one I'm on. The thin ones are other ones that we've scanned. And you can see down here a list of APs. 5 gig and 2.4 gig bands, and the underlined one is the one I'm associated with. I'm sorry it's a little bit small, but that's about the biggest I can get on this screen. So I am going to take a little run around, and a couple of things may happen here. What you should see is a few handover events, which is the whole point of it. What you may see is, as it hands over, it disconnects, and my little mirroring app drops, in which case I'll have to hook it back up when I come back in. But I'm just going to take a quick run around the building and see what we can generate. Excuse the heavy breathing. Man. So what do we see? I had to go a long way to get a hand over here. But essentially, we saw a point here where that little tooth tells us we moved from one AP to another. This tells us we moved channels. And what we want to see is that we're going to a good AP every time, and that we're going to a better AP when we get a low signal strength. So in this case, we didn't really have a low signal strength beforehand, but we did a handover, and we got a slightly better one. Then it dropped off a bit down to here. Handover doesn't look a heck of a lot better when we moved to channel 1 there, but actually it worked because we're going a little bit higher. This is the minus 60 level, I think, here. And then we eventually dropped off. I had to go all the way down to the restaurant for this. And we did a handover and popped back up again on channel 11, come along. So that sort of shows you what's going on. Some of it's due to the client, and some of it's due to the network. And I'll try and tell you what I think is important about this a little bit later. So let me switch to the slides. There we go. So I'm just going to run through a whole bunch of things that I think are important for client devices on Wi-Fi, and talk about the state of the art, and talk about what these darn things should be doing, and why all the device vendors should come and talk to people like me and make better Wi-Fi devices. But the first slide actually talks about why they don't. And here we are in a slightly jaundiced or even cynical view. I think it was Boy George who said cynicism is not a very nice quality, but so let's just call it skepticism. You've got to follow the money in mobile devices, and the money, of course, leads from a consumer back to and generally an operator that provides the phone, and then back to the device builder and vendor, and then back to the Wi-Fi chip and the supplier of the Wi-Fi driver. Nowhere in there do you see enterprise networks. And I would say generally the consumer does not buy a phone figuring, I want to get a phone that works well on my enterprise network. If we can get to that point, then obviously there'll be many more drivers to get the sort of stuff that we want into these phones. But at the moment, we don't see an awful lot. Sometimes things happen that are really good for the enterprise. I think Wi-Fi calling is the latest and most significant of those. But generally, it's been a bit of an uphill struggle to get features the enterprise is interested in into mobile devices. And I think it's primarily because of this. So what we see is that certainly until a couple of years ago, if you walked into Apple, you walked into Google, probably MediaTek, and you started talking about what's going on in Wi-Fi, they would have two things to say. They would say, is what you're proposing going to improve my battery life? And then they would say, when Sergey Brin takes his phone home and wants to connect to his home AP, is it going to be better or worse than it is today? That was very, very narrowly what they were interested in. And that's my picture on the left there. What we want to see is behavior in an enterprise network, which for these purposes means many, many APs all offering the same SSID, which you're supposed to roam between. That's what we're trying to get into. So as I point out here, and I do have a lot of words on these slides, I've tried to make them as big a font as possible. I apologize if you can't read all of it. But we're beginning to see some movement here. And certainly in the last 12 months, we've seen movement from Apple, and we've seen movement in the Android world. And I'll bring those things up as we come to them. First of all, talk about power and battery life. So battery life is a sort of a two-edged thing from our point of view. We have some good technology in Wi-Fi to improve battery power, battery life, but it's not all been implemented. The things that we have seen implemented are these normal legacy power save features up the top here, which are very effective, but effectively the device says, I'm going to sleep, the AP recognizes that, and then while the device is asleep with its radio turned off, it just buffers up all the downlink frames that come to it, and then it advertises in the DTIM to say, we got traffic for you, number 5, and then number 5 device comes up and says, give me traffic, and gets it, and then it goes to sleep again. So that works very well. It does have some side effects that we don't like so much. Here's the second method that we would like to see implemented. It's called UAPSD, which is a horrible acronym. I used to remember what it was. Let me see. User asynchronous power save delivery. Yeah. I'm not going to waste more time on that because, because no one needs to know what it means. But here we go. So this is useful within your beacon interval. And we developed it part of 11E back in 2002 maybe. And the whole object here is that you can go to sleep for periods of less than the beacon interval. And the same sort of mechanism applies. So you say, I'm going to sleep. The AP buffers up any traffic that comes while you're sleeping. Then you wake up and you say, do you have traffic for me? And if there is traffic, then you get it. Generally, this worked pretty well for voice, at least with the older style codecs, because when you have a downlink frame, you also have an uplink frame. So if the frames come at the same rate, then you're in good shape. Because when you offer a frame here, that's a trigger to get a frame down. And there's a little bit of extra delay there up to that sort of buffering interval. But generally, if you're working on a codec with 20 millisecond packet intervals, you're OK. So this is nice. It works pretty well. I tested it years ago on BlackBerrys, and I think I was getting sort of 30% improvements, something like that. It's not implemented, and I'll come to why in a couple of slides. But it's actually quite difficult to do this in a mobile device. The side effects that we, as Wi-Fi people, don't like about this, of course, are that when mobile devices go to sleep on us, things can change and state can get mismatched. And especially if devices move to an area under a new AP, before they wake up, things can get all confused. Generally, that's been worked out in practical terms. Not completely, though. We still see the odd problem with that. The other thing that tends to happen is that when devices think they're in good shape, they go to sleep for long, long periods. And that means that when they wake up, things definitely have changed a lot. And we see that quite a lot in the modern Apple devices in particular. So we'd like to see these devices more aware of their environment and more aware of their environment on a regular basis. And that runs rather counter to the way they're getting better battery life at the moment. Quality of service, QoS. Something else out of 11E, something that's really useful. WMM is very effective up until you get very high levels of traffic, even though it's a fairly simple mechanism, just relying on tweaking the contention parameters. But there's a problem when you start to do it in mobile devices, and I've tried to explain on the slide where these problems are. Primarily what's going on is that the app is responsible for figuring out what QoS it requires, what priority it needs. App developers don't know anything about QoS, generally. And so they don't bother. That's the primary problem here. There's a secondary problem, which is that in the operating systems, both iOS and Android, they've been rather obscure about how to call out a priority. You can do it in Android, but you need to go and put a parameter in when you open the socket. And the parameter is exactly what Broadcom passes up from the driver. It's a rather obscure figure. It doesn't map, well, it does map, but it's not obviously a WMM priority. So I've seen very few apps that actually implement quality of service. This affects us because the part of the call that's going from the device on the uplink towards the AP, that part is dependent entirely on what's coming in the way of markings and behavior on the phone. You can influence it a certain amount, and we do, again, with symmetrical codecs, with periodic codecs, because downlink traffic and uplink traffic tend to be related. So if you start to control the downlink traffic, then you can get QoS effectively on the uplink. But it's still quite a problem. And Apple FaceTime, certainly until quite recently, did not even use a QoS priority when it started up. I haven't looked in the last 6 months, but they should be able to do that. That's an Apple app on an Apple device, and they should be able to handle that. The question?
So what's worse, not implementing it or implementing it incorrectly, like Apple did for their software updates, right? They tagged everything EF, voice priority, and so we started seeing software updates coming in the voice priority queues. Pick your poison. What's the right answer, right? Those that don't do it at all and leave it up to us as Wi-Fi people to prioritize correctly, or those that implement it incorrectly and and we just simply assume because it's tagged voice, it's actually voice.
Okay, so the question was, or the remark was that Apple, I think you said recently, for their software updates, give them voice priority. And what should we do about that? I would argue that, number one, we want to get our QoS right in our networks. So that's what we should be doing. And then number two, if there are devices or apps or situations where they don't behave right, then we need to deal with those as exceptions, which gives us something to do, obviously.
If we're dealing with exceptions anyway,
yeah.
Why not just take the burden away from the app developer and say, don't do anything, we'll handle it. If we're just going to override what the applications are doing anyway, why not just remove the burden from the app developers and say, don't worry about it, we get it, because we're going to have to be contending with those who are going to screw it up. Let's just deal with it on the infrastructure side of the house, right? Let's just deal with it in application visibility or deep packet inspection, and then screw the app developers. We'll just fix it on the back end.
Right. I don't know if everyone heard that, but the point was that if we're going to get in there and deal with individual situations, then why don't we just do it all on the network side? And I think, from my point of view, we already have the features generally in networks to police this everywhere except that link, the uplink from the phone to the network, to the AP over the air. We can't deal with that explicitly anyway. So once it hits the AP on the uplink, we can re-tag, and we do and we should, and it's fairly easy to put in rules for that. Especially if you can identify applications, protocols. Downlink, you can do the same thing all the way, so that's fine. It's just that first bit coming from the phone that's the difficult bit.
Yeah, I guess so you have a smartphone, it's doing all kinds of things. It's doing some voice and some, pushing some data up in the background. So if your phone's not tagging the voice as voice, then it's, it's going to compete with that data going upstream. So that's maybe one more argument to have the application tag the traffic appropriately on the up.
Yeah, I think the station has to do this bit. I haven't seen a different way to do that. It would be nice if we could make the OS here do it. If the OS could recognize that this stream, this session is a streaming video or voice session and put on the tags itself. But that's pretty difficult to do in the OS. I would also like to see them do that for UAPSD in particular. UAPSD that we talked about a couple of slides ago is an even more difficult problem because the amount of information that needs to be signaled between the app and the OS is a lot greater. It would be much easier if the OS would bite that off and say, well, I can see a periodic stream. I think it's probably high priority. I'm going to start applying UAPSD to that. Hasn't been done yet. Hasn't been done yet. So there we are on QoS. The situation is pretty good from the overall network point of view, but from the device point of view, that uplink part is still not practically fixed, in my opinion. Talk a little about location. There's a whole lot to talk about in location. There's very busy marketing people at the moment talking about location. If you come to Airheads, I'm going to give a talk about technologies, not a marketing talk, and all the different ones, and my opinion at least of what they're good for and how good they are. But here's one that's coming in with the standards, and I mention it here because it's one that does require standards. It requires something on both sides, something on both sides of the link, the AP and the client. This is usually known as round-trip time RTT. There are various other names. The IEEE, in their wisdom, call it fine timing measurement, FTM, and it's going into 11MC. It relies on measuring time, and measuring time to give you distance. So you need the speed of light in the middle there, and then you can figure it out. The difficult part is that you're measuring very, very small time intervals, of course. We're talking about a foot per nanosecond for the speed of light. 1/3 of a meter if you're in sensible units. So 1/3 of a meter per nanosecond. So if I can measure to 10 nanoseconds, what have I got? 3 meters, something like that. If I'm looking at a round trip, then and I'm measuring to 10 nanoseconds, then maybe I'm down in the 1.5 meter range. And you should be able to get there. Should be able to get there. We've seen demos, going back more than a year, and we've been able to get them in our lab as well, that go down to that sort of meter accuracy. So what's going on? There's a little protocol that goes with it, and the little protocol essentially says, do some measurements with me, and then the other end says, okay, here's my measurement frame, and then there's an ACK for that, and then the other end sends back a frame that says, these are the timestamps associated with those two frames. So what we end up with are 4 timestamps. And these are local timestamps, of course, so it doesn't really matter which end starts it, but we end up with a timestamp for the beginning, a timestamp for when it was received over here, a timestamp for when the ACK was sent back, and then a timestamp for when the ACK was received. But each end only knows 2 of the timestamps. So to make this a protocol and be able to get all the timestamps in one place, because you can obviously subtract these and get the round trip time, then you just need to do that. But we need the protocol to send a pair of timestamps from one end to the other, and that's what it's doing. There's a whole lot of complicated stuff that goes with this in terms of doing bursts and periodic bursts and things like that, which is going to get, I think, a little bit esoteric once we get it into networks. But these are coming along. They are in the chips now. They're not super sophisticated yet. The next generation of chip, they will be questioned.
I may have missed what you said. This is called 802.11mc, right? That's part of the standard is 802.11mc. Is that what we're talking about here?
Yes. So 802.11mc, this is going into 11mc. 11mc is what they call a maintenance update, which is essentially where they take a whole bunch of amendments that were made since the last one, which was what, 2012? 802.11, 2012, I think. And they take all the subsequent amendments, which are individual Delta packages, and they fold it in so you get a big new 802.11. But what's happening is that we're taking the opportunity to add some stuff to make all this work in MC. So it'll come out as 802.11 2015 or something like that. It was already in there from 11V. It was called something a little bit different, but in 11V it had a 10 nanosecond granularity on the measurement, and we're now getting down to, I think we made it 0.1 because we figure that's more accurate than we're ever going to see in the next, let's say, 10 years from a chip. So, have I got another slide on that? Yeah. So FTM is something that requires 2 ends, as I said, and both ends have to have the protocol. Otherwise, it won't work. And that's why I've talked about it here. A lot of other things like angle of arrival that only require one end to deal with things. It should be coming in. We have seen meter, sub-meter accuracy, but that does require some repeated measurements and some averaging. So we'll have to see in practice what it does, obviously battery life questions. It should be very useful from my point of view, because even though it may not be much more accurate, and I think it will be, but even though it may not be much more accurate than RSSI, the accuracy should not degrade over distance. If you can measure to 5 nanoseconds, 6 nanoseconds, you've got 2 meters, and that's the same whether you're measuring a 5-meter distance or a 50-meter distance. So that's a pretty neat check on the RSSI figure. Because, of course, RSSI, once you get, in my book, beyond, I don't know, 15 meters, you could be anywhere, pretty much. There's a couple of other things that are interesting about this. We need a protocol that also gets us the location of the AP, if you're doing it from client to AP, because all we're measuring is a distance here. And the distance doesn't give you a location. It just allows you to triangulate off a couple of APs. But I think that should be a pretty useful technique if we can get it in the chips and if we can see the results. It's in Android. If you look in the Android code, you'll be able to pick it out. It is a hidden function in Android, so you need to be able to program around those things. OK, DFS. Chuck talked yesterday about DFS. I'm not going to add very much to that, except to say we believe that we should all be using DFS unless you've tried it and you've seen that there are triggers, and triggers occurring in a fairly frequent interval. It's good for a whole variety of reasons, mostly because it gets us more channels, of course. It's also good because it shows the FCC that we're using the spectrum we have. So when we go and ask for more spectrum, they may look a little more favorably on us, because that's an issue right now. We'll move on from there. But DFS is good stuff. And most of the devices you'll see out there, the popular vendors have been doing it for maybe 2 years now. Certainly Samsung, Apple. Five gig band. Again, this is pretty old news. Nearly everything is 5 gig capable now in the way of cell phones and tablets anyway. The big question is, how much does it favor 5 gig versus 2.4 and vice versa? Generally, everything is moving to favoring 5 gigahertz. I think Apple, we had a little bit of a regression fairly recently in one of the iPads, but otherwise it's doing all right. Passpoint. I think Dave Wright talked about Passpoint yesterday, so I won't go into all the details, except to say that this is a very, very useful function. And it's useful because it provides a pre-authentication way of finding things out about the network. And the reason it's, or the way it's being used in Passpoint, primarily, is to find out what service providers you can reach through that network. But there are many other possible uses of this, as I'm sure you can figure out looking at that. In fact, there's a new 11AQ, which I think has been championed by Apple, that modifies ANQP here to allow all sorts of service discovery protocols, primarily probably MDNS from my point of view, because that's the one I like. So you'll be able to do that, again, pre-association. You'll be able to come up to an AP and say, what services are you offering behind that AP before you try and associate. Really neat stuff. The other thing I'd like to mention here is that you can set this sort of thing up today. And the way you set it up is to point your radius back to a hub provider, and there's a whole bunch of them. There's BSG in Texas, there's Acurus out of Dublin, many others. And these guys have connections into the HLRs, forgive the old terminology, or the AAA servers of all the cellular carriers. So if you go to Acurus, you can just point your radius there, and if you come up with a Singtel SIM or something, it will send it off to Singtel, get it authenticated for you, get the answer back, .1x, and then you can get the device on the network, which is really neat. So that's with one connection. Question?
From a security perspective, this just screams honeypot. What protection mechanisms are in place to prevent me from spinning up and impersonating AT&T and saying, I'm just going to collect every AT&T device in this infrastructure, or in this area?
Right. The question was, this looks like a honeypot. What's to stop me impersonating an AT&T network and just collecting credentials and so on from people who try and connect? We're using .1x here, so we're not revealing anything until the authentication is complete. And I think all the usual EAP safeguards are operative here. Everything's operating on either EAP, TLS, TTLS, SIM, or AKA prime. So if, for instance, we tried to authenticate a SIM and we didn't have the right AAA server, then very early in the EAP SIM process, it would fail because I didn't have the network side. Dave. Please.
So I was just going to say with release 2 of Passpoint, it also is introducing a PKI that the Wi-Fi Alliance has put in place. So the actual issue with the honeypot was probably more on the provisioning side, and so that's now going to be authenticated by the client before they connect to a provisioning server. So, and it's not just a service provider technology. So you said service providers, Peter. I'd say authentication providers on the back end. So.
You're on my deaf side there, but I'm going to give you 10 out of 10 for that. Thank you, Dave. Okay, so what did I say? Coming in, you can do that. You can set up today. If you wanted to work with a carrier today, you've probably got to do a commercial agreement. It's interesting that while in practice I can make it all work just by pointing my radius to a hub guy, the operators still look at this as an operator-to-operator roaming mechanism, and it should be a much, much wider one than that. I'm hopeful it will be over time. But pre-association information is pretty neat. Should be able to use it for lots of things. Obviously, in hotspots, that'll get us past Whisper and open unencrypted traffic, which is something we desperately want to see. All right, let me move on and talk about Handover, something I've been looking at for way more years than I'd care to admit, which doesn't necessarily make me wiser. In fact, it may not be relevant at all. So let's just move on. So I've got a picture here that sort of shows how handovers work, or worked at least up till maybe 18 months ago. And the general situation was we're associated to an AP, probably with a pretty decent signal strength. We start moving, signal strength drops off. Things go pretty quickly because AP is generally at walking pace, so let's say 20 seconds apart. So eventually the signal strength gets weak enough that we figure we ought to do something about it. And the thing that we do about it is to send out probe requests on different channels, which takes a while because you've got to go off channel, send your probe requests, listen for a bit, come back on channel, do what you were doing on channel, and then go off on the next channel. It takes a while to go through channels like that. But anyway, at the end of that, you get a picture of what's around, and then you can figure out that you want to associate to one, and then you associate. So that's pretty much what happens today, and typically by the time you associate, you've gone past the darn thing. And it's time to look for the next one, because as I said, this is happening every 20, 30 seconds. Not so efficient. I've found that I need to develop my own tools to look at these things the way I like. May just be contrariness. But this is my packet analysis tool, which takes a PCAP or PKT. These bits are the things to watch. This is the downlink signal strength, or SNR if you like, measured at the device. So I walk around like Keith with, although I don't have his neat tray, with sniffer in one hand, phone in the other. Sometimes I find if I put a white lab coat on, people think I'm doing something interesting. Otherwise, they just think I'm crackers. And my 18-year-old would agree with you there. But 18-year-olds are tough critics, aren't they? So what you see as you walk around, and this is time and distance on the horizontal side, is that you're associated to an AP, the signal strength maybe goes up because you're going closer to it, And then as you walk down the corridor, eventually you're going away from it, and then eventually you want to see a handover. And hopefully you hand over to something that's a little bit higher, hopefully a lot higher. And then the same thing repeats. You may go closer to it, you eventually go away from it, and you need to jump to the next one. The sort of things that are interesting here are how often it's sending probe requests. Those red squares at the bottom show you that probe requests are going out, and the little blue things, little sort of showers here, are the probe responses sorted by signal strength. So what we want to see is that as we're getting down into, let's say, the 30 dB SNR range, and certainly down to the 25 dB range, we see some probe requests going out. We see a good signal strength on a probe response, say something up here, and then we see a handover subsequently that gets you onto the best possible AP that you saw in the probe responses. And typically, the problems that we see are that things just happen too late. And I could show you this for all kinds of phones, but they're all pretty similar. Once you get below, I don't know, 20 dB SNR, then retries, which is this line, both up and down, start to get really bad. And my conclusion from this is that you think you've got an outage during your handover here, from when you sent your reauthentication message to when you got your key messages. But what you've actually got is lousy performance, lots of retries, low signal strength, dropped packets for some seconds or tens of seconds before that, and then you got the outage. And that's what you should be looking at. And there's a lot of work going on right now in Wi-Fi Alliance, actually, to rejuvenate what we used to call Voice Enterprise. Voice Enterprise came out when? A long time ago now, 3 years ago. And while a number of AP vendors have certified Voice Enterprise, to my knowledge, no device vendors have certified to Voice Enterprise. And you can draw your own conclusions as to why. My conclusion is that it's too onerous. There's a lot of work in it from the device side, and they don't see the payback. The product managers can't say, we'll sell more phones because we do this. So what we're doing now is sort of revamping the problem, and there's something in Wi-Fi Alliance led by Mark Hamilton from SpectraLink, but it was actually kicked off by Microsoft, the Link group, where they're taking another look at, can we get a certification that pushes devices towards better behavior in moving between APs, handover stuff. There's another picture, there's another picture. So you see the same sort of sawtooth behavior, and this is a not very good phone because this is the 20 dB line down here. You think you've got a connection, but it's pretty much useless. And of course, retries on the air are bad things, as Chuck has mentioned a number of times. So we got that tool, we got the tool that I showed you at the beginning, and that's the way I look at these things. So what we're trying to incorporate, sorry, question? Whoa. Shot over, shot out.
You took a look at sticky clients, which I know tends to be a problem with voice and with phones. I'm wondering if you also took a look at roaming aggressive clients, which tend to be more in the PC, laptop base, where I've maybe have two APs that I've got, both I have reasonably good signal strength from, and the device is perpetually bouncing between one and the other, even instead of just staying put. I wonder if you've looked at that problem as well, because I've actually seen quite a bit of that. Yeah. More in the PC laptop kind of arena.
So the point is ping-ponging between APs, overactive clients, over-aggressive, if you want to call it that. We look at that from the network side. I don't think it's nearly as big a problem as what I just showed you, incidentally. And I think it's much easier to solve. We look at it from the network side, and we use our sort of selective blindness features to try and stop it if it's happening too much. But generally, we look to the client to just keep a hysteresis timer there. Andrew?
Yeah, Peter, I was going to say that's usually a matter of the error rate or retransmission threshold being reached, which is typical of very dirty air, right? So high AP transmit power is typically where you see that. Where you see the client. Most client drivers these days will not bounce between unless they're reaching some sort of error or retransmission.
Thank you, Andrew. So I'm just going to run through these functions very quickly with little pictures, because you've probably heard about them. You may not have figured out what they actually do. I always find I need a picture or I can't understand much at all. Let's see if I can explain a picture, especially one that I drew myself. Here we go. So 11R. 11R is fast PSS transition. And that basically cuts short the authentication protocol. So instead of doing a full MS chat v2 when you show up at the new AP, which is pretty typical today, and which involves maybe 50 frames an ax on the air, depending on how big your certs are and stuff, this gets it down to the order of 10. So what happens is that right at the beginning, when you first authenticate, they generate these sort of master keys. I call it the red set or R0. And then that allows both the network side and the client side from the master key to generate a set of intermediate keys, the R1 keys, which are the ones that are actually used to generate the pairwise keys, which are the ones that are actually used. So we never expose the R0 key, we never expose the R1 key, we only get the stuff that's generated off it. On the AP side, we have to push these keys ahead. So there's a little protocol. I think in Aruba, we push them ahead to the closest 6 APs as measured over the air. But I may be wrong on that. On the client side, there's a well-known derivation protocol that allows them to do that. So essentially now, because we've got this set of keys that we can generate for any new AP, anytime our client gets to a new AP, it just takes the red key, generates the yellow key, and then generates the pairwise key off that should work on that AP. So you don't go through all the who am I early stages of authentication, because it's already been done back here and we know who you are. It's actually very similar to OKC, opportunistic key caching, but the cryptographers like it a little bit better, quite a lot better actually in the IEEE. Has pretty much the same effect. You're getting down to 10 frames instead of 50. So that's a great thing. That will speed up the re-authentication part. So you show up at a new AP, you can exchange your 10 frames, get onto it. That should bring you down. Certainly OKC brings you down into the order of 20 to 15 milliseconds versus about 200 to 300 for a full MS chat. The other things that we're very interested in come out of 11V and 11K. We've got a neighbor report. So the neighbor report allows the network to tell the client, these are my neighboring APs, and some information about them. And I put some of the information up here. So it gives you neighboring APs, channel, obviously very important, channel, some security stuff so you can figure out if it's part of the same family. Pretty obvious, I think. And a beacon offset. The beacon offset says, from my beacon, you go so many TUs off, and you'll find the beacon of this guy. So with that information, we are giving the client all it needs to go off at precisely the right moment, fairly precisely anyway, to let's say 10 milliseconds, to listen on a certain channel, and it should pick up a beacon of a neighboring AP, which is really cool because it means they can go passive on finding handover candidates versus being active and sending out all those probe requests on all those channels that we talked about earlier.
How does the phone know what direction it's moving in?
Say again?
How does the phone know what direction it's moving in, right? If I'm surrounded by 3 or 4 APs at different distances.
Great question. How does the phone know which direction it's moving in? I'm solving that from the network point of view because I think the phone's too dumb. But, yeah. So the network knows a lot about history of clients and what a different client did in this situation before. The client could find that out if it had a cloud backend, but generally it won't know it. But certainly if things are moving fast, you could make this better. But even without that, getting this information versus having to scan an awful lot of channels and then try and figure out what's the best AP?
Yeah, I agree. If you could limit it to say, okay, I'm going to scan these handful of channels because I know that I'm going to hit one of these.
Yes.
Right. Then you could obviously speed up that whole process quite a bit.
Yeah. So the idea that we have anyway, or one of the ideas, is to prioritize this list so that we figure the one that you really ought to go to is the first one, but go down the list. That relies on the client vendors writing that in as well, but I've been telling them that for quite a while, that's what we want to do. The length of the list is dependent on what the AP decides to send out, so we can send a very short list. We can send one if we like. Apple, I think, says they read the first 6. Okay, so that's neighbor report, and that should be a huge improvement. Beacon report is actually something that we like to use. It allows the client to tell the AP, these are the signal strengths that I hear various other AP beacons at, and that allows us to figure out where the client is, although, of course, we get equivalent information from the network. There's a channel report. Probably won't be used much if people are using this, but that tells you what channels are in use in this network. PSS Transition Management. PSS Transition Management is really neat because it's a directed handover. It allows the AP to tell the client, move to this AP, and now. And that's very cool. I think I talk about it in a couple of slides, so let's move on. That was the neighbor report. No, maybe I'll talk about it here. No, I'll go on. So here's the sort of behavior that we want to see on the bottom. I've shown you enough of those sawtooth diagrams and what they degenerate into before. What we want to see is passive scanning, but more frequent passive scanning. Because one of the problems right now is that the devices just aren't aware of their environment. They don't become updated often enough on their situation. If they knew that they were moving away from the current AP, then they'd start looking for a new one. But generally, they don't take any action until the signal strength has dropped to a pretty low rate. What they should, and part of that, I believe anyway, is because of the focus on battery life and not wanting to send probe requests, because they're expensive. So we get down to this, and if you can use your neighbor report and go passive, then you should be able to get updates far more frequently, which means you've got a better picture of what's going on, which means you can make better handover decisions. And that's what we want to see. So the whole picture should look a little more like this. Oops. So there we are. Generally, we're just getting updates from the neighbor report, so we know all the way through what's likely to be my best AP handover candidate. And that can change as you move, but you've got a pretty good list and an ordered list when the time comes for you to move.
Quick question on that.
Yeah.
Have you found, because neighbor reports are action frames, the client has to actively request it from the AP.
Yeah.
I've found that a lot of them just do it initially when they associate, and they don't do it continuously.
Yes, I agree. At the moment, clients generally get a neighbor report when they first associate to an AP, and then they don't update it much. We need to see more. Okay, this is why PSS Transition Management is useful. What happens right now, and I think everyone does some form of this from the AP side, is that when you figure you've got a sticky client or you want to nudge it and get it onto a new AP, you send a deauth. And that's a very, very blunt instrument, but it's about the only thing you have in the 802.11 protocol. And then after the deauth, the client's supposed to figure out where it should go next, and there's nothing to tell it exactly where it should go next, so you have to selectively suppress probe responses from APs, that kind of thing. With the PSS Transition Management frame, we don't need to do that. We can just go straight out and send a PSS transition management instruction, and then the device should move to the new AP. And we are seeing very good take-up of that feature. So let me just jump to that part of it, because I've got 5 minutes left. There we go. So you'll see these things. You'll see these things categorized as 11K, 11R. 11R is pretty straightforward. 11K is a huge document. It's 1,000 pages long or something. But generally, people, when they say 11K, they mean the neighbor report. And sometimes they mean PSS transition management, but generally that would be 11V. So just be aware of the nomenclature there. iOS is pretty good on 11K and 11R. And there we are. That's the slide. And Samsung is pretty good now. At least I've got 11R and 11V up there, which would be the PSS transition management. So that's good news, right? That is very, very useful, and it's fairly recent, and it shows that things are moving more or less in the direction that we'd like to see. I've got a couple of things just to finish up with. Random MAC addresses are coming in, mostly for privacy purposes, I believe, although tough for me to get inside the heads of the guys in Cupertino. But obviously, if you're starting to send out a probe request and it's got your real MAC address in, and it's got, especially if it's directed and it's got an SSID that you're looking for in, then you're giving away information that you probably wouldn't choose to give away if it wasn't part of the protocol. So what they're doing is, when you're not associated and not ready to associate, we're switching to random MAC addresses, and these are generally locally administered, certainly on the iOS devices, and you should see these prefixes, and that should let you figure out if that's what you're seeing or not. We will see that on some other platforms. I'm not sure about Android, but certainly look for it coming up on some of the Microsoft devices. Maybe identical, may not be quite the same, but something similar. And let me just finish on Wi-Fi calling, because I think this is a really, really big milestone for the industry. I don't know if Dave talked about it yesterday, but Wi-Fi calling is a sort of a wave, a second wave of the UMA thing, and I actually just looked out my UMA white papers, 2008, 2009. But T-Mobile brought it in back then because they were very interested in carrying voice calls, SMS, as well as data over Wi-Fi. It's coming back, and it's coming back primarily driven, obviously, by the Apple announcement in iOS 8. The architecture I put up here is the general architecture. It's not necessarily the way everything is implemented today, but it's good enough for our purposes. So essentially, you've got some sort of SIP client in the device, which goes over IP, of course. Then you've got an IPsec tunnel that goes back, and then it goes out through the Wi-Fi. So at this end, the network end, which is an operator, so you need this gateway guy to unpack the IPsec and then feed the stream into the packet gateway, which deals with IP, and then you've got the IMS that deals with SIP. You can do this in a non-VoLTE network. It just means you have separate stacks up here. But the important thing from our point of view is that you're using your mobile phone number. That's the difference between this and over the top, of course. The difference from the network point of view, Wi-Fi network, is that you can now build your own coverage. You can build your own coverage for cell phone coverage holes, and with Wi-Fi, you are completely carrier independent. You put up one hotspot, and it will cover phones from all the carriers by the end of 2015. We've certainly seen announcements from AT&T, Verizon, Sprint, and T-Mobile already there in this country, and a whole bunch, obviously, outside this country. So this is going to be very interesting when you start looking at DAS, and you start looking at small cells, picocells, femtocells, and other alternative ways. I'm a big believer in Wi-Fi. I believe that Wi-Fi is sort of like the IP protocol in the 90s, that it will just move forward and steamroll everything in its way because it works and because it has a lot of momentum. And I think we're very lucky to be on the right side of history here. I think Dave brought up my quote, not a unique quote, yesterday from a couple of years ago. We're definitely moving towards a world where we only need the cellular network to fill in the gaps between Wi-Fi. And that's going to be pretty cool, I think, for all of us. OK, I'm going to wrap up. Thank you.